Good afternoon, everyone. I think first of all, thank you for staying till the last session. I think we should give everyone a round of applause for staying till the last. And so today, what we're going to share with you is really this whole topic of AI for good. You saw one of the initiatives being launched during Satya's keynote. Let me just switch to the slides. And so today, specifically out of the 3 programs, we're going to share with you some of the work that we have been doing in using AI for advancing some of Earth's toughest challenges, right? And therefore, if you recap what you have seen earlier, at Ignite this year, we shared about AI for humanitarian action. But prior to this, if you've been looking at the past 18 months, we actually have been launching a lot of AI for Good initiative. And the goal there is really to empower many of us, right, me, you, everyone, in being able to engage and use AI in more meaningful ways. And the goal is very simple, right, to create a more sustainable and more accessible world. And if you look at the breadth of technologies that you have seen across the 5 days of Ignite, whether it's AI, whether it's advancement in the cloud, whether it's advancement in hardware, and so on and so forth, this is changing the way that we live, we learn, and we work. And one of the fascinating things about this transformation is it's actually creating tremendous opportunities, of course, for the work that we do for our companies. But at the same time, if you reflect on it, we all have a huge responsibility, right? We are all technologists, and therefore it's important for us to be able to use technology to both, meet, of course, your KPIs, which is really important, but at the same time, think about how we can use it to solve some of these challenges, right? Whether it's in your free time, whether it's with a non-profit that you work with, and so on and so forth. And so if you boil down everything that you have seen in the past 5 days, it's really 3 things that you should think about. There has been tremendous advancements in algorithms, and this pace of innovation in algorithms is just going to keep happening, right? At the same time, of course, at all these kind of technology conferences, you see advancements in hardware, right? Whether it is with GPUs, whether it's with FPGAs, and so on and so forth, hardware is continuously, innovations is happening in that space. And of course, the third piece is really the fact that, hey, we all collect a lot of data, right? Whether it's in the companies that we work with, the non-profit that we work with, and so on and so forth, there's tremendous amount of data being collected, not just about enterprises, right? But data collected about the species around the world, data collected around water, climate, and so on and so forth. And therefore, if we put all this together, it will allow us to use technology to solve really some of these challenges. And today, what we're going to share with you is some of the projects that we've been working on jointly with Esri. But at the same time, we'll also share with you where we're heading, right? And if you're interested in some of these projects, we'll give you a call to action on how we can participate in it. Sounds good? Right. And so the story, let me first start off with a story. And all these discussions about AI that you have been seeing, or specifically in deep learning, really started off with this thing that is not new, right? And a convolution neural network today, in the context of deep learning, really allows you to do a lot of amazing stuff, from being able to do image classification to even audio classification, and people have been using it and continuously innovating in this space. Now, so a trivia for everyone in the room is, after all the sessions that we've been to and all the tech conferences and all the AI discussions that you might have, how long does it take to train a deep learning model, like a convolution neural net that you saw earlier? Less than a minute. Awesome. That's the aspiration that we're getting to, but thank you. Right? And of course, we want to get to less than a minute, and we're actually getting close to that. Right? And one of the reasons why I asked this question is the following. Just to illustrate and provide you with a data point on how fast the space is innovating. Now, if you speak to me about before 2017, and you say, hey, I want to train a really deep convolution neural network, it probably takes days, right? But 2017 was an amazing year. In April 2017, Facebook, with some of their open source hardware called Big Basin, demonstrated that you could train ImageNet, which is a very classical data set used for image classification, or the basis for image classification, in an hour. And in fact, that piece of work in April 2017 kicked off a whole conversation and innovation in the distributed deep learning space. Now, a few months later, Another group, which is a university, showed that without GPUs, you could train an ImageNet model for 31 minutes, which is fascinating. And of course, you think the year 2017 is going to end off that way. No, right? It continued innovating, and towards the end of 2017, ImageNet training took just about 15 minutes, right? And this is done by a group in Japan. And the point that we're trying to get to is just look at the pace of innovation. It's what's happening in 2017 alone. For a really simple task, not exactly, but let's suppose it's a really simple task of training a deep neural network for image classification. The time is half every time there's an innovation, right? And in fact, as this gentleman called out, 2018, just in July this year, a group in China, right, demonstrated that they could do ImageNet training using ResNet in 6.6 minutes. And I'm sure the year has not ended, right? It's just September. We'll get to the goal of 1 minute. But what is also fascinating is the following. Today, we used to think that, hey, all these innovations that's happening here needs to be either a big research lab, right, or a big company that's doing that. And there's already been a lot of science in the community that shows that today with public cloud hardware, without so many GPUs and without so much compute, you are able to do it as well. Meaning we could do it on our way back to wherever we come from, right? And you should be able to train it within 15, 31 minutes. And that is the point. The point is the power is no longer an excuse to say, hey, we can't have all this infrastructure because we don't have it, right? The power is now available for all of us to do this. And that's why it's important, because then we can use all this to solve a lot of these fun problems, right? And therefore, AI for Earth was really a program that was conceived by the Chief Environmental Officer, Lucas Joppa, many years ago. In fact, he was at Microsoft Research for many years before he became the Chief Environmental Officer. And it's a program that looks at, one, providing access to all this technology so that all of us can solve some of these challenges. What is more important is we can dream and we are willing to do it, right? Two is, of course, education, being able to work with every one of us in this room to understand why a lot of the Earth resources are being depleted, food production is not going as fast as we want it to be, and why this is a pressing problem, and why technology and AI can solve all of this, right, in the right way, and if you use in the right hand. And the last piece of it is, well, whether it's deep learning community or any of these technology communities that we are all a part of, we have tremendous creativity, and therefore we can continuously innovate. And through all this innovation, it's going to move the state of art, right? And so what is AI for Earth? And why is this important, right? AI for Earth is really a program that is designed to empower non-profit, right? And it may not even be a non-profit organization. It could be an individual that cares about the Earth and saving the Earth. With technology, with grants, with access to some of the engineering teams at Microsoft, so that you can empower both people as well as the non-profit organization to solve some of these global environmental challenges. And it really focuses on a few areas. One, which is agriculture. How many of you have been to the expo and been down to the expo? You see at expo, at the center of the expo, there's this huge booth, right? And you can actually practice precision agriculture there through a project called FarmBits. Right? And therefore, we've been spending a lot of time on agriculture. I'm going to share with you some of the projects in the area. And we're actually getting a lot of interesting benefits from there. For example, right, today, all of us need to eat. In fact, after this session, I'm sure we'll all be heading off for lunch. We are all hungry. But the point is, today, if we want to feed the world rapidly growing population, it's a no-brainer, right? The farmers and the organization that's producing the food, regardless of what kind of food, must produce more food. But we live on planet Earth, and on planet Earth, there's only limited land. Earth is not going to double the size in 2 years, right? And therefore, with limited resources, how can we then enable all these farmers around the world to be able to sow more effectively, to be able to create more production on all this limited land? And we believe that AI can help a lot in that. And FarmBits is essentially one of the projects in that area. Now, the other area that we look at is really water. Now, water is very important, and therefore, how can we conserve and protect all this fresh water supply that we have? is super important and top of our mind as well. And biodiversity, we're going to show you a few projects that we've been working on understanding the biodiversity on Earth, but more importantly, protecting the animals that might eventually get endangered. And what is also interesting there is we might think about protecting endangered animals as not our business, someone else's business. But we have seen and we've worked with a lot of people, whether it's within Microsoft and outside of Microsoft, that has been using technology to solve this problem, even though, it is not their day job, right? Which is fascinating. And of course, the last piece, which I think all of us have seen, is climate change has indeed been an issue that we all need to think about. And how can we use AI to reduce all these challenges, right, of climate change on communities? So if you look at AI for Earth program in general, it's really divided into these 4 areas. And what is interesting is since this program started, we're about 1.5 years old now. We have given grants across the world, right, to about 100+ grantees. And the list is still growing. And today, every one of us in this room, if you have a passion for using AI to solve some of these challenges, we invite everyone to apply for a grant. Of course, you have to put in the justification, there's a proposal, right? But we give grants not just to non-profit organizations. We give grants not just to universities and so on and so forth. We give grants to anyone that has a passion to solve this problem with us, right? And so, to put all this in perspective and just to show you why AI is such an important component of saving the world, let's try a simple game. All right, and to do that, I'm going to share with you the story of the snow leopard. How many of you have cuddled a snow leopard before? Now, in fact, I hear some laughter. In fact, what happened is this whole snow leopard trust was really started, and of course, there's a lot of such organizations around the world. This was started as a result of 2 cubs being brought to the Woodland Zoo in Washington State. Right? And in fact, last October, we celebrated the first birth of a cub, and everyone was there cuddling the cub and so on and so forth. But snow leopard is an interesting species. In the areas where they operate around the world, snow leopard is known as the ghost of the mountain. And for specific groups in the world, they are actually seen as sacred animals, right? And as sacred animals, they are really a really important component of the entire ecosystem of both the locals that's in the area, but at the same time, they are tremendously important to the folks or the people in the Himalayan region, right? Now, and so we work with the Snow Leopard Trust to use AI, in this case, image classification models, to detect the snow leopard. Because in order to protect a species like this, you must first find them and understanding their habitat, where they operate, and so on and so forth. And so just to illustrate to you why AI is important and why, we all want to experience what a snow leopard researcher does, let's play a simple game. Now, somewhere in this picture, there is a snow leopard. Now, every time I do this, someone was saying the snow leopard might be hiding behind a rock. Anyone can find a snow leopard. Now, as you're looking at it, let me continue the story. Today, for example, the group that we work with, one of the researchers is called Costa. He spent about 6 to 8 years on his PhD just on snow leopard, right? And every single day, he has to pour through lots of photos like this to identify the snow leopard so that he can then understand their habitat, how they move, and so on and so forth. And so, in fact, when we worked with him last year, one of the things that he shared with us is that he actually spent time looking at the snow leopard photos than family photos because he needed to finish his PhD. And the point there is when we met him, we said, well, what if technology can help? And what if AI can help? And it turns out that in order to be able to detect this, in the deep learning community, this is known as a fine-grained computer vision problem. And if we can start teaching algorithms to know that this is the bounding box where the snow leopard is, then the next time I show you the photo again, now all of us can actually detect snow leopards, right? Because I have taught you how to do that. And the point here is, well, what if he has all this, every time he does a survey, and he has all these traps, which I'm going to show you in a while. These traps are distributed all around the area where he's doing his study. Each time it collects millions of images. And we call it the snow leopard going up to take the selfie. Now, in actual fact, it's not, right? They might pass by it, you might get a glimpse of it, and so on and so forth. And he brings all these images down so that he can then analyze them. So one of the things that we built with him last year was that he took all these photos that he has in his collection over the 6 to 9 years that he was doing his PhD. He uploaded it to Azure storage. And what we did was that there's an Azure function, right, that gets triggered when all this gets uploaded, right? And as a result, by the time he uploads, right, the most lengthy time is really the uploading. Then in his blob storage, he gets 2 folders. 1, high probable snow leopards. 2, no snow leopards. So it reduces the huge amount of pictures that he has to do and process and view to maybe less than 20% of it. Right? And in fact, one of the things that is fascinating as he was doing his research is that all the photos that he has other animals except snow leopard. Guess what kind of animals he sees most often? Goats, mountain goats. Right? And somehow the mountain goats are just curious about the camera traps. So the mountain goat will go up, look at the camera trap, and so on and so forth. And so this helps him reduce, right, the time taken for him to identify the snow leopard. And of course, each one of the photos that gets taken, right, is geotagged to where the camera trap is. The time, the location are all there. And so now he can understand the habitat better. Now, sounds familiar. Now, whether this is used for snow leopards or whether this is used for example, manufacturing, the technology is the same. Being able to detect and being able to classify. Right, I'm going to show you some of the work that we've been doing in this area, specifically on biodiversity monitoring. So one of the companies that we work with is a company called iNaturalist. In fact, iNaturalist is a fascinating app that you can download, whether it's on iOS and Android today. It's an app ready for you to download today. And it allows us to say, well, all of us can play a part in trying to understand the species diversity on the planet. In fact, when I came to Orlando, right, I had my iNaturalist app. I can understand all the fauna or all the flora and the flowers that's around this area that's interesting. As I walk back to my hotel in the night and I see an interesting thing, I can actually take a picture of it and contribute to this growing database, if you will, of information about animals, flowers, and so on and so forth, right? And the point there is once you have that, you now have a really diverse data set of trying to understand animal population across the world. Right? And so iNaturalist has been working with us for a while, the AI for Earth program, on trying to turn this into APIs that all of us can use. Now, just to give you a perspective, iNaturalist today is a non-Microsoft company that we work with. It has an online community of what we call citizen data scientists that has been recording data on the distribution of Earth biodiversity. Greater than, right now, there's about 500,000 people, 6 million observation is growing by the day, and about 120,000 distinct species identified, right? And this is fascinating. And so this app, we've been working with them in order to improve it. Now, so this app shows you how you could provide information using the iNaturalist app. And just to give you an illustration of how it works, anytime you bring the app out and you see an animal, whether it's a rabbit that is at your backyard, you know, or a deer that you see when you're driving back home, or some animals that you see somewhere, you take a picture of it. It's going to ask you for a location. It's going to ask you to say, hey, what do you think this animal is? You're going to give your best judgment. Right? It's going to share with you what are the other people who have seen similar animals like. Right? And then they're going to provide more inputs. So this crowdsourcing way of doing data labeling, right? Being able to then use all these labels that it have to be able to train algorithms becomes something now easily achievable, and all of us can do it, right? And once you are done with that, of course, then this is provided back to the community. In fact, iNaturalist, for the past 2 years, has been running this big competition at a conference called CVPR, which is a premier computer vision conference. And this iNaturalist database is just growing. Now, to show you why iNaturalist is important, I wanted to show you a demo, right? Now, so this was an app that we built on, once you have all this data that's labeled using an app like iNaturalist, what can you do with it? So right now, what you see here is a sample site that we built, right? And what is this sample site about? This sample site is really about, well, if you have all this iNaturalist data, how can you train a machine learning model to be able to then understand the animals that you see and so on and so forth, right? So I could go explore, or I could upload a picture that I've And so right now, this page that you see here, every single image here is not taken by us. We pull it from Bing using the Bing APIs. You could search for any animal that you want, any animals that you're interested in. Anyone? Sorry? Octopus. Oh, that's a hard one. That's a good one, but it's a hard one. Oops. Octopus. Did I spell it correctly? No, we couldn't find octopus. Any other animal? Sorry? Kiwi. Oh, wow, that's interesting. Oops. Let me just refresh the site. Yep, we didn't find kiwi. Let's do one last one. If not, I'm going to find my favorite rabbit. Anyone? Lima. Oh, L-I-M-A? L-E-M-U-R. Is that right? Ooh, okay, we did find some lima, right? And so, once this is done, we can click on each one of this, and when we click predict any one of this, what is happening is it sends to a back-end API that we have constructed. And you see that now we identified the bounding box around the lemur. And more importantly, we tell you this could be a koala because the algorithm is not perfect. It could be a monkey, it could be a long-eared owl, it could be a baboon, and it could be a spider monkey, right? And the reason why we continuously work with organizations like, for example, iNaturalist is this is going to get better, right? We are not saying this is perfect, and that's the reason why we did not launch this as a product. But this is a species classification API that today, after this conference, if you're interested to build against, drop us an email and we can actually make it available to you as a way for you to play with stuff, right? But more importantly, this allows you to then be able to do species classification very quickly. And so to show you how it looks like, any one of you familiar with cognitive services? Or you have used some of it? Yeah. So cognitive services is really a set of pre-trained models that Microsoft has wrapped around APIs, RESTful APIs that you can access. Now the same species recognition APIs that you see here is also wrapped as well. And therefore, if you download any of the sample code for cognitive service, and if you change it to this AI for Earth API URL with a subscription key, now you can suddenly now detect animals in the programs that you write, right? And so you could create other kinds of apps like iNaturalist and so on and so forth. So this is going to read off from a file called demos AI for Earth, pick number 2, and let's see what it is. So this is a picture of zebras that was taken at one of the zoos, right? So what we're going to do here is we're going to send this picture that you see here to the AI for Earth species classification API. And if we go to the API itself, let me do a right click and go to the definition of it. You'll see that I put a few breakpoints, which is the point where after we send it to an API, it comes back with a set of results. And let me try to run this. So right now what is happening is we're invoking an API, just that how you invoke any of these cognitive services is coming back with a set of results, and it's sorted based on the most probable animal or species that you have seen, right? And it also gives you other suggestions as well. So if I were to step through this, you'll see that we'll have identified a top species as the one that is highest in the enumeration. And if you look at the result, we think it is a zebra. But at the same time, this enumeration that comes back also shows you the top 5 results. So if I continue running this, you'll see that while we think it's a zebra, that's the most highest probability animal or species that we have found. It could be a mustang, it could be an ostrich, it could be a kudu. And the point there is, as more data we have from all this crowdsourcing effort, the algorithms will get better, right? And that's the reason why we say, hey, these APIs are available today, and we really invite every one of you to use the iNaturalist app to help us continue advance the state of art in this, right? So with that, let's switch on to another important topic, which is precision conservation. And before we get into precision conservation and what it is, we wanted to show you one of the videos from the customer that we've been working with for a while called Chesapeake Bay Conservancy. And this was really a joint project between Microsoft, Esri, and Chesapeake Bay Conservancy. And let's roll the video.
I've been a waterman on the Chesapeake Bay since 1995. When you're out there on the water every day for that long, you see how things have changed. It's hard knowing there's nothing you can do but watch.
My name is Bob Ingersoll, and I'm a farmer. The demand for our kind of work is only going up, and we're constantly looking at how to expand our yield without stripping the land or polluting the bay.
The Chesapeake Conservancy has been focused on creating tools that help answer some of these questions.
In the infancy of the Chesapeake Bay program, scientists built a scale physical model of the bay to understand how processes worked and to simulate potential solutions. A lot has changed since then, and technology has been the catalyst. The Chesapeake Conservancy has been a pioneer in the field of precision conservation, getting the right practices in the right places, but it hasn't always been easy. Until recently, land cover data was only available at 30 meters resolution and represented what the landscape looked like 7 years ago. Not great for precision planning. We raised the support and spent 18 months working with our partners to create a 1-meter land cover database for the Chesapeake Bay program. This unprecedented project took a lot of effort and massive computing power. Now we are working with Microsoft and using AI and deep learning to accelerate our work, both in the Chesapeake and across the country. Our collaboration is aimed at providing partners with the information they need to make informed decisions.
Now, so one of the things that you'll see that is enabled by all of this is really this concept called land cover mapping. Now, to distill it out into its simplest term, it is you have all this satellite imagery, right? And today, there's a lot of manual efforts by experts, right? Sounds familiar? Remember the snow leopard story I shared earlier? There's a lot of this manual efforts by experts to understand, hey, this part of the land is really a road, this part of the land is really vegetation, this is where all the water area is, and so on and so forth. And so, in order to be able to do this more efficiently, AI can help. And today, AI has tremendous capabilities to be able to use deep learning algorithms to understand the respective pixels in a satellite image, right? And most of these satellite images are 4-band, which is RGB and near infrared. And so with all this information, you can actually use a lot of technology and AI to be able to understand every single pixel, right? And so this was really the case when we started working with Chesapeake Bay. Is they were trying to analyze about 100K miles or square miles of their what is known as the watershed area. It's about 2 terabytes of information. It took them 18 months by experts to manually create the map. Now, by the time they finished this in December 2016, the map is outdated because land has continued to evolve. And so we think, hey, there's a better way to do it, right? And so one of the things that we did with them is really to build a land cover mapping solution, which later on we're going to show you in a while. But the point here is being able to use algorithms to process all this satellite imagery at an amazing speed, right? So that it doesn't take months, but rather it takes days or even hours to produce a fully automated map of not just Chesapeake Bay, the whole of the United States. And of course, our aspiration is eventually to be able to do automated land cover for the rest of the world. We're not there yet. This is something that we're working towards. Now, if you take all this information I'm sharing with you right now and distill it to its very core element, this is essentially a very exciting area which has both AI for good interest. It also has interesting commercial interests as well. And so this space is really to say, well, you have all this data. This data are geospatial data. You have massive amount of compute available in the cloud. And you have AI algorithms. If you combine all of this together, you will be able to do amazing things. And of course, here shows you a project life cycle of what is happening under the hood. And so S3 and Microsoft together, we have been thinking deeply about this problem. And more importantly, making this available to you to get started, right? And therefore, with that, I'm going to invite Rex to show you some of the work they've been doing together on trying to use deep learning, a VM on Azure, which we call the Azure VM, right? All together in order to help you do land cover mapping. In this case, this was a use case that we did with NOAA, and I'm going to hand it over to Rex to share with you.
Great, thanks, Wee. Great, so some of the knowledge that we gained when working on the Chesapeake Bay Conservancy project and working with Microsoft and some of the technology around that, we've been able to take some of that information and apply it to a sort of a broader extent. And so part of that effort is part of this deep learning land cover classification effort with NOAA, working with ArcGIS, the ArcGIS platform, which is Esri's platform for working with GIS data, and with Azure, and working on some of the Azure capabilities that are available as part of Microsoft's platform. So just to start, I want to take a look at a problem, a problem that NOAA has right now where they want to be able to take existing imagery that they have available, and they want to take that imagery and they want to be able to provide a mechanism, or currently they're using a mechanism to sort of manually and through a variety of different workflows create a land cover mapping. And so basically we needed a study area to target. And so we started with a relatively large region, a little over 2,000 square miles. This is Snohomish County, just north of Seattle. They're coming with a variety of basically nationwide high-resolution imagery at 1 meter resolution, NAPE imagery, so 4-band imagery, as we talked about earlier. This is imagery that's available for download today from NOAA's website. And so they want to be able to take this imagery, and they want to be able to optimize the process for land cover, for defining land cover classifications. Currently, they have a process for labeling billions of pixels within this study area, and this would be just over 11 billion pixels, using an ensemble of different techniques, right, to produce this land cover map. Some of this process is automated, some of this is manual. In general, it takes weeks, actually, for this size of study area to come up with a land cover mapping solution, to come up with basically an image or a raster with labeled pixels that define really 6 different output classes that they can use then in further analysis. What they're looking to be able to do is to optimize and to reduce the amount of time to come up with a land cover map. And so this is input data in our study area with NOAA. And we want to be able to take a look at the approach. So how can we tackle this with deep learning? So the approach that we're going to take here is working with a deep, fully convolutional neural network, right? A CNN. We're going to use CNN in future slides here to reference this process. And we want to be able to segment this imagery and utilize our ground truth, basically the labeled pixels that NOAA uses today that take a couple of weeks to come up with. We want to use that as really a baseline. And so we want to be able to build out a network using deep learning capabilities to create a model that we can use to create or to basically accelerate this process so that it's not a manual or a combination of automated and manual processes, and that we can generate a result much faster. So there's a variety of different techniques that we're using here. One is residual unit architecture that we're leveraging Microsoft Research in this case. This is the same type of technique that's used in medical imaging. It's good to find cancer. It'd also be good to classify land cover. So it's a very rich model or rich mechanism for using within a deep learning process. We've got a set of different connections that we want to make here when we're training our model. We want to be able to add those together so that we can supplement this model as we train it. We've got a variety of different layers that we're bringing in as part of convolutions, so we're not losing any data. This is a lossless process, right? So the number of input pixels and output pixels are the same. The goal here is that we want it to be faster. We don't want it to take weeks. We want it to take much less than that, actually, and we'd like to optimize the amount of time that it takes to work in this case. We also want more efficient use of resources, and so instead of taking both physical and virtual resources, we want to be able to optimize the use of resources and costs associated with that too. Ideally, we'd like the results to be just as accurate, if not better, and so we want to be able to take that into consideration. The key here is that this is all being done on a Azure-AI VM that is hosted as part of Azure on the Azure platform. It includes Esri technology as well as a variety of other different technologies for building out your model, training your model, and then viewing the results. We'll take a closer look at that here in a little bit. So what were the results? Just really quickly, what were the results that we saw? Well, if we're using the input imagery, the NAPE imagery that's coming from NOAA, we're using their ground truth that took a couple weeks to come up with. And then we evaluate that as a baseline and trying to figure if, once we train our model, to get it to a point where we have better than 90% accuracy. That's our first goal. And so we were able to get an overall accuracy of about 92%. It took about 2 to 3 days to train the model to get to a point where we had this level of accuracy. This was good enough, actually, to continue to process and at least reevaluate additional inputs that we had within the model. There were some notable differences here that we need to tackle going forward, but this was an initial review of being able to evaluate and use these inputs to determine or to come up with a model that we could use. There was some confusion here between different classification types, such as forest and scrub. Some of the roads that were covered by forested areas, by vegetation, were difficult. The model wasn't able to determine that quite so easily. But one thing to keep in mind here is that there were errors in the ground truth, right? The baseline, there were some errors there too, so we need to account for and consider that as well. So with that, let's go ahead and take a look at some of the results here initially. This is going to animate through really just the two inputs and then the output from the model. So we have aerial imagery, ground truth, which is the labeled pixels from NOAA's current process, and then we also have the CNN classified output, which is the output from our model. So in some cases, we had some good agreement between these two, right? The ground truth and the CNN model actually came up quite well. This is a subdivision. We can see some of the forested areas there in green, some of the impervious surfaces in white, and then some open areas actually in brown. We can see that there's a pretty good match there in most cases, and so we had some pretty good accuracy there for most of the portions of the aerial image. Now in this case, what we can see is that some of the open areas that actually have either open or had scrub were not classified correctly as part of ground truth. And so our neural network, our deep learning process, our model was able to more accurately classify that based upon the results from the image and using the training that we had provided. And so this was a better scenario here, and we can see the difference here between ground truth and classified there on the right. Here's another issue I mentioned before, that it was a little more difficult for the model itself to recognize roads that were covered by vegetation. And so we can see here there's a road that goes top to bottom in this image, and that the ground truth actually sees. With ground truth, we're taking in a variety of different inputs, and we can see that impervious surface, which is white, is a fairly clean line. With our model, we're seeing that some of the areas that are covered by vegetation are a little bit more difficult to see, so something that we need to take a look at to further train our model. This is kind of interesting. There are a set of piers on a lake in this area, and in the ground truth, the piers were missed. They weren't considered part of the land cover. With the model, it was able to see those and classify those as structures. So it was interesting that our model actually detected that. Also, during the training of the model, we were able to determine or at least filter out different areas that were shadowed, but we were able to determine whether or not there was a shadow based upon the structure within the image, and we were able to accurately classify this, in this case, as an open area. In some cases, though, models were misclassified. In this case, some of the shadows were misclassified in the model. And so in this case, the shadow was classified as open water. And so again, maybe some additional training, some additional inputs here to train our model in a better way to more accurately represent what we're seeing in the imagery. Right. What we can see here is that we have some basically a discrepancy here in the type of vegetation, looking at both scrub and grassland. And we can see that the ground truth area is accurately classified this, and we need to further train and maybe look into other ways of training our model to get better accuracy here too, so discrepancy. And then one last comparison here. We can see that there's a bit of a sparse forest within the aerial image, and then as we see the ground truth compared to the CNN classified, it looks like there's a discrepancy here. It's unclear exactly what the actual vegetation is, and so being able to more accurately describe this, or maybe get some additional ground-based information to determine a better model or a better result in this case. What we found overall, though, is that the result of this evaluation was pretty good. There's a couple things that we could use to improve this. Now, as I said, it took about 2 to 3 days to actually train the model, right, to get to a point where we had at least 90% accuracy. Once we had the model in place, it took about 1 to 2 hours to actually generate land cover classification raster, right, labeled pixels. So compare that to 2 to 3 weeks, 1 to 2 hours, considerably less, and just over 90% accuracy. What we could do, though, is we could actually get better input data. So being able to work with updated ground truth, maybe better input data to train the models going forward. We could also work with other surfaces, other areas or regions that have different types of land cover classifications, such as impervious surfaces, land cover imagery that actually includes roads, to better train our models to recognize some of the other classification types that it had some difficulty with. We'd like to actually supplement our model probably with a deeper understanding of some of the other structures that are within the aerial imagery to give it a better understanding too. So there's some things that we can do here to actually deliver optimize our model for a more accurate or a better result. So the key here is that we were able to basically come up with a reasonably accurate or highly accurate result and reduce the amount of time actually to deliver this labeled land cover classification raster. Now, one thing I want to highlight here is that although I walked through really the process here and some of the results that we saw, and we saw that we were able to optimize this process and reduce the amount of resources that were necessary to be able to deliver this result, I want to highlight the fact that this was all built on top of the Azure platform, and it was built on top of some of the Esri technology that's available to be able to process geographic information and imagery. So the one item here that we worked with in this specific process was the Azure-AI VM. This is a data science VM that's on Azure. It's available today, so you can spin one of these up today. And on that VM, you get a set of applications and frameworks pre-installed for you, and so that you can start working with and building out your models. It's got, basically it has a variety of different technologies, including Python, the cognitive toolkit, the additional IDEs to be able to take advantage of and work with your Python environment to train your model. It also includes ArcGIS Pro, which is Esri's desktop product for being able to process and visualize geographic information. ArcPy is also a technology that we use to work within Python to be able to generate results and access geographic data. Now, all this work that we did today was built on top of the Cognitive Toolkit, Microsoft's Cognitive Toolkit. And all of the results in this case were actually built on top of this VM that's available within Azure. One thing I want to note here is although that was done on a desktop, the work that was achieved here could also be done through the Azure Batch-AI process, or you could actually take this model that you've created and you could deploy this in a Docker container, host it in an Azure Kubernetes cluster, and then that model would be available for additional insight, and then be able to access that model from another Esri product, ArcGIS Enterprise. ArcGIS Enterprise is really our server product. It's also available and can be hosted in Azure. From ArcGIS Enterprise, you can create a service endpoint that enables access to the model that you've created. You might provide a mechanism for inputting imagery and generating results, land cover classification results, and making those available to either your enterprise or your constituents. So a variety of different capabilities here, all built on top of Azure, all built on top of Microsoft technology that Esri provides for you to be able to take advantage of some of these deep learning capabilities. With that, I'm going to hand it back to Wee, who's going to take a look at a demo of getting started with a Azure-AI VM.
Yep, so before we get into the demo, I think you have heard a lot about some of the work that we've been doing on land cover mapping. And you say, hey, what if I want to get started? Is it like only Esri or Microsoft can do it? Or today, if we have access to an Azure VM, can all of us do it? That's one. Two is, even if we give you a VM, you're going to say, hey, how do you go about doing this thing called pixel level or being able to do land cover mapping? Is it really hard? Is there something that, tutorials that's going to help me get started, and so on and so forth? And so what I'm going to show you next is really the fact that, hey, today if you have access to a VM, we actually all can get started. And so if you do not have an Azure account, I'm sure everyone will know that, hey, you could get a free Azure account for a limited period of time. And once you have an Azure account and you log on to the Azure portal, you can do all sorts of wonderful stuff with Azure, but one of the things that you can do is you can provision a Azure-AI VM. So if you search for Azure-AI, you'll see this thing here called the Azure-AI Data Science Virtual Machine. And one of the things that we also realize is that even if we give you a VM with all these deep learning tools that's on it, you might say, hey, what if I need ArcGIS? Right? So between Microsoft and Esri, we've been spending a lot of time trying to think about how can we make this experience frictionless. And so on this VM, once you provision it, which we're going to show you in a while, you're going to get all this in together with all the script and all the tutorials on one of the files or one of the folders on the VM. And therefore, you should be able to get started and being able to do land cover mapping, right? And so if I was to start Azure-AI Data Science Virtual Machine, you read through what it is. And if you click Create, it's going to ask you for some information. So I could say, hey, this is an Ignite Azure-AI VM. I'm going to give it some name. In this case, let's call it AI for Earth Admin. It's going to ask me for some password. I'm going to copy some password here. And of course, it's going to say what subscription you're going to use it. I'm going to use the AI for Earth Engineering subscription. It's going to say what resource group, right? So in this case, I've created one resource group, which I call Ignite, I think. Let me look for it. If not, I'll create a new resource group. Okay, let me create a new resource group. Let's call this Ignite 2018 Demo 2. That was the backup plan. And if you click OK, what is going to happen right now, as we're all familiar with virtual machine creation, right, is it's going to ask you, hey, what kind of things do you need? In this case, because if you're going to play with the VM, you might need to train some deep learning algorithm. So one of the things that we default to is a DS4, but you could then choose NC6 or whatever that is needed if it's available in the region. And once this is done, right, I'm going to click OK. And it's going to move on to the next step to say, hey, am I ready to create? Now, once all this validation is done and I click Create, now in minutes, as we all are already familiar with, is going to provision a virtual machine for you in the cloud, right? And in this case, this is a Azure-AI VM. And if I click Create, the VM gets created, right? And once the VM gets created, you can then RDP into it. And you see a VM that looks like this, right? It has all the tools for you to get started with deep learning, for you to do data science. But at the same time, all the tutorials are all loaded onto the VM. And one of the things that you notice is that ArcGIS is already default installed on it. And then once you build the model, the tutorial is going to guide you on how you can consume the model using ArcGIS Pro. Right? And with that, let me show you what it looks like once you start working with this. Right? And with that, I'm going to hand it back to Rex to show what is on the VM. So Azure-AI Data Science Virtual Machine is a virtual machine that's available today. And I encourage everyone to get started. And this comes with all the tools, Visual Studio Code, data ingestion tool, connecting to different kinds of data platforms, right? Whether it's Cosmos DB or whether it's Azure SQL and so on and so forth. But it also provides you with ArcGIS Pro installed on the machine, ready for you to get started. And let's see what kind of magic you can do once you have all these things installed on a Azure-AI VM.
Right. Great, thanks, Wee. So what we saw there is just really a practical way for getting started with your sort of deep learning process here, working with Microsoft technology, building on top of Azure, but taking advantage of Esri technology here when working with your geospatial data. So what we're looking at right now is this is a Azure-AI VM I just created a couple days ago. This is the same VM that we used to work through the workflow or the process that I talked about earlier with NOAA. Right? This is also the same VM we used for Chesapeake Bay. Right? So it's the same technology, the same capabilities. All the tools that are available to you are already pre-installed and available in this VM, so it's ready for you to go. It's already building on top of an NV VM in Azure, so already pre-enabled for GPU compute. So you can take advantage of those capabilities right off the bat. What I'd like to do here is I'm just going to walk through a couple of the sort of the technical capabilities that I talked about in the NOAA project. Some of the work that was done here to be able to craft the gathering of the data, the basically building of the input data sets, and then training the model. So what I've opened up here is Visual Studio Code. Now this is some Python code that we used. Now in the actual process itself, we ran Python from the command line. Granted, you could bring this up, you could use this in a variety of different IDEs. We happen to do it from the command line. I'm bringing it up in Visual Studio Code here so that you can actually see that this is another mechanism for visualizing your Python code and being able to manage, manipulate, and craft this logic. Now this is a Python script that was created and uses ArcPy. ArcPy is part of Esri's platform for being able to access and work with geospatial data. What it's doing is it's taking in NAPE imagery from NOAA, It's also taking in the ground truth labeled raster that we talked about before that they derived after a couple of weeks of work. It's basically breaking that up into batches, and it's going to prepare that data for training. And so once we have those patches created, we're going to bring in another Python script. This actually comes from Microsoft Research, what I talked about before. It brings in some of the technology and the knowledge there, and it integrates that within a Python script that allows us to iterate through our training process. Right, so this training process, in this case, will use the model provided by Microsoft Research. It's also built on top of the Cognitive Toolkit, Microsoft's Cognitive Toolkit, and so we'll see a number of different references there and leveraging that for deep learning. Once this process is running, and as I mentioned, this takes about 2 to 3 days. We're working on a VM here that's got 4 GPUs, right? Of course, if you throw more hardware at it, it's going to operate a lot faster. We saw that a little bit earlier in Wee's presentation about throwing more hardware at some of these processes to reduce the amount of training time. Of course, we're looking at cost effectiveness too, right? So we want to make sure that we have a nice cost-effective process here as well. So this is the script that we'll be running in Python. As it's running, a log is generated, and what I've got here is a TensorBoard dashboard to show the results of that training process over time. And what we can see here is that we want to be able to see how well these predicted values, the percentage of those predicted values, are correctly predicted over time. And so as we get to a point here where our metrics looking at close to below 10% basically here, so we're getting over 90% accuracy, we're looking at a good model, something that we want to work with, right? So there's one way of keeping track of as your model's working and processing, you can actually see how it's progressing and how well it's doing. Of course, if it wasn't progressing well, we could stop it, we could readjust some of the variables, and we could make changes as needed. Now, as I mentioned, this took a couple of days, but once we had an output, what I could do at that point is I could then visualize this information within ArcGIS Pro. So what I'll do next is I'll bring up ArcGIS Pro. This is pre-installed. This is just an example. Obviously, it's a professional GIS desktop application, so it has the ability to work with a variety of different data formats. What I'm showing here is sort of a practical look at some of the inputs that were used. This first layer here that we're looking at right now is one of the NAPE images, or the 4-band images that NOAA provides today. And I can see this is an area here that we covered actually in the slides earlier, where it had a set of piers. You can see them off to the right. If I hide that, we can take a look at the image that was created. Right, so this is the ground truth labeled pixels that was created by NOAA over a 2 to 3 weeks period. We can see the different labels applied to different areas based upon their manual and automated process. And then we want to be able to really evaluate and compare how this looks with, in this case, a TIFF. This is the output from our evaluation when using the model. So once we use the model, we input aerial imagery, we output or we generate a new raster with labeled pixels. So this is our land cover classifications from our model. And we can see that this is another raster. We've not lost any resolution here. It's the same number of pixels. We just have different classifications. And so if I tick this on and off, we can see here is right now we're looking at ground truth. Right, if I turn off the ground truth, now we're looking at the result from our evaluation using our model, right? And so we can see there's some very close relationships here. Now what's interesting is this was just for Snohomish County. We took that model and we applied it to a number of other counties. And if I slip over to a map here, so Snohomish is just north of Seattle. We've added in a number of other counties here, such as Island and King County. Now I said it took about 90 minutes basically to complete this analysis for Snohomish. It was about 1 to 2 hours for the other counties too. So you can imagine, if each of those counties took 2 or 3 weeks previously, well, now you're looking at 1 to 2 hours. So something that might have taken, almost 2 months now takes a day, right? So what we can see there is that if we're getting a reasonable amount of accuracy, and this actually is be able to use much more efficiently, then you can see that being able to determine land cover much more accurately over a shorter period of time, and be able to evaluate change detection and other evaluations that go on with land cover classification evaluation. You can see that this reduces the amount of time it takes to actually generate results that are usable going forward. With that, I'll hand it back to Wee.
Thank you. So thanks a lot, Rex. Now, at this point, every single thing that we showed you, from being able to do land cover mapping, the work that we had with Chesapeake Bay, to the point where you can actually do exactly what we showed you on stage. This is all available on the Azure-AI VM, and we encourage everyone to get started. Now, the question I wanted to get to now is, well, we have seen all this. And if we say, well, we have all this satellite imagery, how fast do you think can you do land cover mapping for all the data that's in all the satellite imagery, which we call named imagery, right, across the whole of the United States? How fast do you think we can do land cover mapping? Remember earlier on it was 18 months, right? We showed you some of this. This might take several hours to train. But if once we have trained the model and want to apply this model, what is the state of art and how far can we push the limit? So just to give you some data points, data for the whole of the United States from a satellite imagery perspective ranges from about 20 terabytes to about 40 terabytes, depending on how you cut the data. Question to you is, how fast do you think we can do inference on it and do land cover mapping? 1 minute. We are working towards that as well. What other guesses? Days. 1 day. That's pretty good estimate, thank you. Now, and one of the things that you've been hearing about, right, since the Build conference this year is we announced some of the work that we've been doing on this project called Project Brainwave, which is the ability for you to then take all these deep learning models and get them onto the FPGAs. And FPGAs is going to enable you to be able to do inference really quickly. Right? And therefore, we took the same piece of work that you saw earlier, right, and we started applying it using Project Brainwave, and we loaded the model onto Project Brainwave. And it took 10 minutes to process about 20 terabytes of data, which is about 200 million images. Right? And this is how the architecture looks like. Now, what is also interesting is this work is reproducible if you have the named imagery. Right? If you go to the URL that I'm going to share with you in the previous slide, you'll see aka.ms AI for a brainwave land cover mapping. If you go there, again, we provide you with all the technical information on how we can reproduce this on using the FPGAs that's already available on Azure, right? So that's pretty exciting. Now, the next thing that we're going to show before we end off land cover mapping is really some of the work that we've been doing, experimental projects that internally that we've been playing with some of the garage team, and this is the work done with the Vancouver garage. And remember, we started off this session by saying, hey, AI and us being technologies, right, we're able to use both AI and technology to advance and solve some of these toughest challenges. All it takes is that little sprinkle of creativity on it. So what can you do, given all this power on your hand, given all this satellite imagery that you have, what other things can you do with it? So the next video I'm going to show, really a short one, is really some work that I've been doing, a really early experimental project, to say, well, if you have satellite imagery, I could build an app like this. And what does this app do is it can look at satellite imagery, and today satellite imagery could look something like this. And then now you're able to use it to be able to detect not just the animals that's on the ground, you could use it to detect the boats, you could use it to detect the roads, and so on and so forth. And this has tremendous impact, especially around humanitarian needs. Right? Today, after one of this hurricane hit, one of the things that you really need to do is to go in and figure out the damage at the area. Right? And so technologies like this is now doable. And more importantly, what you're seeing is an early prototype that we built that allows you to then deploy the model not in the cloud. Because if you go to a lot of these areas where a hurricane hits or some situation occurs, Wi-Fi is not a given. And therefore, you want models to run on the intelligent edge. And this was just an early prototype that we have built just to illustrate that. And this was built by a team of about 6 interns from the Vancouver garage. And these are just the possibilities. And the point I'm showing you this, not because this project is interesting, is the fact that all of us, we build applications, we build web applications, we build iOS, we build Android, and all kinds of applications. Now, today, together as a community, we can actually build applications like this and make this available, right? And now we can truly use AI and technology to advance a lot of these needs, right? And use AI for good. So that was a quick peek. Let me quickly switch gear to FarmBits. If you've been to the expo, you've seen a lot of information about FarmBits. Just to provide you with a little bit of data point, if you look at some of the data from, say, the UN, by 2050, one of the things that we know is that the demand for food is expected to outpace production by over 70%. And therefore, we need to empower farmers with the ability to have, of course, more data, but more importantly, to process all this data that the farmer has, And the goal is the following, to maximize their efficiency, right? And also maximize their yield. So for example, we work with farmers in a state called Andhra Pradesh in India, and they are groundnut farmers. And we had a control group that has no machine learning algorithms, and one that is empowered by machine learning algorithms. So one of the things you might be thinking about is, well, most of the farmers doesn't have access to a PC. They're not going to log on and say, hey, should I do this or that, right? Not possible. But one of the things that the farmer has is a mobile phone. And so for the group that is empowered by the machine learning algorithms, we will give them short messages to say, hey, this is the time you should prepare the land. This is the time you should sow. This is the time you should harvest. And these are the things you should do, right? And we did this comparison about 1.5 years ago with this group of groundnut farmers. And what happened after the project? In fact, we took a long time to collect the final results just because you need to wait for the groundnuts to dry, right, before you know the yield. Just the group that uses machine learning algorithms has a 30% improvement in crop yield. And we also duplicated the same thing for carrots in one of the farms up in Carnation in Washington State. And again, they see a similar improvement in yield, right? And therefore, FarmBits is really a project that empowers farmers to do all of this by doing two things. One, by providing them with low-cost sensors, but most importantly, telling them where they should situate the sensors so that they get the best representative coverage for their farm. Whether it's small farm, big farms, all possible. In fact, we've been looking at even oil plantations as well. And so FarmBits is really a project that was born out of that need. Right? One is, today you could use drones and you fly it across acres and acres of farmland for big farms. And you get satellite imagery, not satellite imagery, drone imagery of the farmland, so you know the terrain of the land and so on and so forth. And then if you fuse this data with the data that's coming from the sensors, it could be temperature, it could be humidity, it could be nutrient, it could be wind speed, and so on and so forth. You create a heat map. And we're all familiar with heat map for enterprise use cases. This will become a heat map for the land. And this heat map is going to tell the farmer exactly which are the areas of the land that needs more attention, which are the areas of the land, right, that they should, do something about it, and so on and so forth. Now, FarmBits right now is a project, not just a Microsoft research project. It's ready for use by everyone. In fact, we have been working with folks globally on deploying FarmBits. And therefore, if you own a farm, like I was talking to some of you during lunch, contact us if you think that FarmBits can help you, right, in trying to use AI to do precision farming. So this just shows you an architecture diagram for FarmBits, which is a combination of drones, some of the advancements that we have in the networking space, and so on and so forth. And this was just a deployment that we had in upstate New York, as well as in Washington State, Carnation. The farm sizes ranges from about 2,000 acres to about 5 acres, respectively. And what we've deployed in all these farms is really the DJI drones for taking the drone imagery. Sensors, in this case, moisture, temperature, pH, and so on and so forth, as well as cameras to capture the state of the farm. Right. Now, all this is actually available. In fact, if you've been to the expo, you actually experience and see some of the portals that we build. And why is this important? Look at this piece of land. From the drone imagery, you get interesting things. You see water puddle, awesome. You see even cow excreta. Right? You see cows, and you see stray cows. Cows that are not supposed to be there, and they are there. The farmers need to figure out and bring the cows back to safety, right? Now, and so this is just a quick overview of FarmBits, and you can read a lot about it if you search for FarmBits on the web. And this is a project ready, and if you have a farm, we encourage you to contact us, and we hope to work with you on that. All right. In fact, the FarmBits project was interesting. It was an article that we wrote in The Economist about 2 years ago, and officials from the state of Andhra Pradesh actually contacted us, and we had the team stationed in Andhra Pradesh for, I think, 3 months just to do the local deployment, and right now we're doing and analyzing some of the results from that effort. Now, the next piece that I'm going to share is a project called Project Premonition. How many of you have been bitten by mosquito before? Awesome, right? And we all think that, hey, with mosquitoes, they bite you, but they do not just bite us. They bite animals as well. So one of the insights in this project is, well, what if all these mosquitoes that you have are your drones? really tiny drones that you can't control. You can't send a signal to them and they move the direction you want. But they do fly and they do operate globally, right? And so if you are able to tap this team of drones, or little mosquitoes if you will, then you can actually use that for biodiversity monitoring. And in fact, they can be used to survey, for example, ecosystems, track wildlife population, and probably use this in a lot of variety. And therefore, Project Premonition was born out of that. In fact, the guy who leads the project, his origin was really in robotics. And at the point in time when he showed us that thing that you see there is a very intelligent camera trap, right, that will get the mosquito in, does image classification, extract DNA samples, and do a lot of wonderful things. We say, hey, are you joking? You're a robotist. You're just trying to find a use case. But it turns out that these traps that we have deployed in some of the locations here, we actually get interesting insights. And every time we find new species of not just mosquitoes, because you usually have a bait. The bait could be anything. Sometimes we use carbon monoxide and so on and so forth, right? But once the mosquito comes in, we take a picture of the mosquito using small cameras inside. It turns out that we actually find new species of insects, if you will. And every time he shows me photos from his excursion, if you will, it always amazes me. And therefore, Project Premonition's challenge is really the following, right? We know we want to use platform for biodiversity monitoring. And we know that if we don't do that, a lot of this species is going to go extinct. And so Project Premonition was really a project that we created in order to understand mosquitoes. I'm going to show you a video of that.
What if we could stop the next epidemic before it happens? What if technology gave us the power to turn this enemy into an ally?
Mosquitoes are the ultimate field biologists, taking blood samples from every animal they bite. Microsoft and its partners are using smart traps to capture mosquitoes and study the DNA they collect. Using the Microsoft Cloud, we can analyze over 100 million pieces of DNA in every sample, so we can identify where diseases come from and how they spread. With the cloud, what used to take 30 days now takes 12 hours, and every second counts. If we can detect new viruses before they spread, we may someday prevent outbreaks before they begin.
We must be passionate, we must be bold, and never stop striving in our desire to make an impact.
So what you saw was really Project Premonition and some of the few deployments that we have. And this really shows you the architecture. And the point we're doing all of this is really the following, right? We have smart trap. That little device that you saw is really the smart trap. And we use CO2, we use white LED lights. And inside, we actually have different kind of sensors to detect mosquitoes, right? But at the same time, we also take a snippet of blood from the mosquito itself. And right now, for example, to date, we have deployed these traps in about 87 experiments globally with 22,000 mosquito landings. Take that for a KPI, right? And so with that, one of the things that we're trying to do is to use this trap, one, to monitor the habitat and wildlife condition. So one is we could use this to understand insect composition. But more importantly, we can actually understand the host animal distribution. For example, right, let me give you an example. The insects get trapped in the trap. We could then extract out the blood, but more importantly, we could then do gene sequencing on each one of the specimen. And if you do metagenomic analysis, you will be able to distill out the DNA composition. And what is fascinating is that 90% of the DNA is the insect, and about 5% of the DNA that gets extracted because of the result of the metagenomic analysis is really from the host animal. And with that information about the host animal, we are then able to infer the biodiversity in a specific region, right? And one thing that I wanted to call out here is, well, you might say, how do you do metagenomic analysis? How can you do it really fast? Now, it turns out that a while back, Microsoft also announced a Microsoft Genomic platform, right? And therefore, a lot of this work on Project Premonition and all this metagenomic analysis was done on the Genomic platform. Fascinating work. Now, with the remaining time, I really want to bring us back to this conversation that we started off. We said, well, it's algorithms, it's hardware, and it's data. And many a times, whether it's an enterprise project or AI for a good project, one thing that you'll hear very often that data scientists will tell you is we do not have enough data, even though we do have a lot of data, but we do not have enough data that's needed to train the models. And so if you think about data, I wanted to end this off with just this little thinking about data. If you can't get the actual data, there's different ways. Like for example, today if you do autonomous driving, you'll never have enough training data to train under all kinds of conditions, all kinds of weather conditions, all kinds of terrain. And so a lot of the companies has been doing simulation. And therefore, one of the things I wanted to show you is we'll also be working with organizations, both within the company and outside the company, to think about how we can do simulation. And so the next project I wanted to show you is really a project called AirSim. It's open source as well, and you can download it. This actually allows you to do simulation of drones across different kind of terrain. And it actually then extracts out information about the segmentation images, right, as well as the actual flight path. And all this information becomes data that are labeled, data that you can now use in your training of your models. So one of the things that we did on the subject of biodiversity is the following. We wanted to identify poachers in some of these national parks. And we want to be able to then figure out what are the paths that the poacher has taken so that we can catch the poachers before they kill some of the animals, right? And of course, you'll never have enough training data of poachers and animals. So one of the things that we did with AirSim, which I'm going to end off this presentation on, is really work that we did using AirSim to simulate a really super realistic environment. In this case, it's the African savanna. Now, that whole simulation I'm going to show you, today you can actually go to GitHub and you can actually download it, and you can also play it as well. So let me show you. So right now what you're seeing here is really a simulated environment of African savanna from a drone perspective. Now you see the animals that's there. We simulate the vehicles that might come from different kinds of personnel that's there, and so on and so forth. And so you see that, hey, even with the animals, later on you're going to see some elephants, I think, as well as alligators. These are all simulated environment, and we can continuously simulate this even as we are talking right now. And this becomes tremendous amount of data that we can blend with the actual footages in order to produce training data for the models for biodiversity monitoring. So you see the alligators, you see the water. Now, and a lot of people have been using this AirSim environment to not just simulate the African savanna. Now I see a herd of elephants. You're going to see some trucks later on. And so simulation and ability to simulate additional training data is super important, but the ability to simulate synthetic data that is as real to the real world, right? AirSim provides you with the ability to do that, right? And so AirSim is also an open source project. I encourage everyone to try it. And with that, I'm going to end off with, well, we started off this talk as an AI for Good talk, right? We showed you a few of these use cases. And as I was saying, all of us have a part to use AI and technology for good. And more importantly, grants are available to support you on that. And so if you or your colleagues or your co-workers or friends that you know are interested to use AI for some of these challenges, we actually encourage you to sign up for the grants, right? And the grants will provide you with access to the engineering team. It will provide you with access to Azure resources as well. But more importantly, like I showed you species classification and so on and so forth. All those APIs are ready for you to consume today in a private preview kind of mode. And therefore, contact us if you're ever interested to try out. Now with that, we end off the session. But before we end off, I'd like to get everyone to give a round of applause because you stayed until the last session, 1:45. So thank you, everyone. Thank you. So with that, yeah, thank you. Thank you for coming to our session. Please submit the evaluation and wish everyone a safe flight home. Thank you. Thanks a lot, everyone. Thank you.
Thank you.